week 4 tutorial session. So we'll be discussing normal shocks today. I hope you have gone through the lectures. Okay, so I'll just brief the basic equations that we use for normal shocks. So here I've considered a very general variable area duct, and here we have a normal shock. So if we can just consider a small control volume around this shock. Okay, so what are the basic equations? Can you help me out? The continuity equation. Yeah, continuity, energy and momentum equations, that is right. So let us say this is part 1 and part 2 of the duct. So what is the continuity equation? Right, so what we will assume is that very close to the shock the area is not changing, because we have considered a very thin area over here, right? So we will neglect any area variations very close to the shock. So then your rho 1 A1 V1 equals rho 2 A2 V2 becomes just so A1 will become equal to A2 very close to the shock, and that's why we can write rho 1 V1 equals rho 2 V2, right? Yeah, and then you can further just manipulate this equation. So for example, you can say P is equal to rho RT, use the state equation, right? And V by A is equal to M. So if I use these equations, and also I know that M is nothing but A is nothing but under root of gamma RT, right? So I can plug in these equations into this equation, rho 1 V1 equals rho 2 V2. What do I get? I hope you've seen this equation, P1 M1. I'm not doing each step, but this is how you will get to this equation. You're familiar with this equation, right? Yeah. Okay, so this is one important equation, and the other one is from the energy equation. So what is the energy equation? No, just the basic energy equation. No, total enthalpy is okay. Total enthalpy is H plus V square by 2, isn't it? And then if you remember, we also had plus Q. So this is, say, in section 1. And then we have H2 plus V2 square by 2 plus W. So what we assume is that there is no heat loss or heat added. Okay, so this is 0, and work is also 0. So this is very important right now. This assumption is very important, because if we don't assume this, the equations will be very different. Okay, and we will come back to this assumption. We'll change our assumptions and we'll let some heat loss occur due to friction, or if some work is being done, then the governing equations will become different, and that will be our Rayleigh and Fan. Okay, so now right now we have this that the total enthalpy remains same across a normal shock. Okay, so from this we can then immediately conclude, because the fluid remains same, there is no change in the composition of the fluid, so we can also write that T01 is equal to T02. And from adiabatic equations we know the expression for T0. T0 is equal to T into 1 plus gamma minus 1 by 2 m square, right? So that gives us the relation between T1 and T2. So we know that across a shock the static temperature changes, stagnation temperature does not change. Okay, so this is very important. Okay, and now what about the momentum equation? Okay, let me write down. Momentum equation is P1 you're saying P1 multiplied to this? No, I'm asking you the very basic governing momentum equation which you would have derived earlier, which is P1 plus rho 1 V1 square is equal to, and we are assuming no gravitational effects and all. So you have this, we have derived this earlier, right? Okay. Okay, so then from here you can again put in your equations. P is equal to rho RT, and so rho you can replace by pressure and temperature, and again we'll use the same relation. V is equal to m under root gamma RT. Okay, so what does that give us? So you must have got this equation. P1 1 plus gamma m1 square is equal to P2 1 plus gamma m2 square. You're aware of this equation? No? Okay. Okay, so this is the momentum equation. This you are aware of, right? Yeah, so what I have simply done here is I've used the state equation, and I've replaced the density. So you see this density term, that I have put in terms of pressure and temperature using the state equation. Okay, and the velocity I have put in again in terms of Mach number and temperature. So that will give you this equation. Okay, do you want me to derive it? Not required. Okay. Okay, so this is a very important equation, because what this tells you, so if I just rearrange this equation now, this is P2 by P1 is equal to 1 plus gamma m1 square by 1 plus gamma m2 square. So what does this tell you? Across a shock, what happens? So I should have started with this. What happens across a shock? The Mach number increases or decreases? It decreases. Exactly. So across a normal shock, the supersonic flow becomes subsonic, right? So if you go back here, m1 is supersonic, m2 is subsonic, m1 is more, so the numerator is more. So what that tells us is P2 is more than P1, which is obvious because shock is nothing but a compression, thermodynamic compression. So we expect that the pressure should increase across a shock, and we get that relation over here from the momentum equation. Okay, so how much the pressure increases we are getting from the momentum equation. Now can you tell me what happens to the temperature? Yeah, so how can we see that? So we saw the energy equation. From there, if I just derive the relation between T2 and T1, that is going to be T2 by T1 will be 1 plus gamma minus 1 by 2 into which Mach number will come in the numerator? m1, right? m1 square, and this whole divided by 1 plus gamma minus 1 by 2 m2 square, right? So that again tells me that since m1 is more, temperature is increasing. Okay. Okay, so we know that static temperature increases, static pressure increases across a shock, stagnation temperature remains same. What happens to the stagnation pressure? Why? Because of loss of energy. So we have seen this relation, if you remember, P02 by P01 is equal to e power minus delta S by R, right? And yeah, so when the entropy increases, stagnation pressure is going to decrease. So what happens in a shock? There is going to be some loss. Okay, now one very important concept is, see, what is a shock strength? How do you define a shock strength? Okay, so you are saying that shock strength is measured by P2 minus P1 by P1. Okay, this is a measure. But what essentially determines the shock strength is the Mach number. Okay, so higher the Mach number, and higher the Mach number difference across the shock, higher is the strength of the shock. Okay, so even this expression, if you see, you can get it in terms of M1, right? So this is going to be a function of M1. So the shock strength is higher if M1 is higher. Now the question is, what happens to the stagnation pressure? So if I have one condition where M1 is say 1.5 and another condition where M1 is 3. So where is the stagnation pressure drop going to be higher? In 3. Why? No, that I understand, but the only relation that we have which tells me the stagnation pressure ratios across a shock is this. So you are saying that the entropy increase is higher if the incoming Mach number is higher. Right. So M1 is also related to the static properties, and when the static properties change abruptly in a short region, when the abrupt change is very high, then the entropy loss will be very high, right? So in this case, your losses will be higher, and hence this drop in the stagnation pressure will also be higher. Okay, so I can say delta P naught across a shock will be higher. Okay, now do you know how to relate the stagnation pressure and the area? No? Okay. So let me do a small an important derivation for you. So I'll start with the area relations. I think you must be aware of this. If not, you can go back and check the derivation. So I'll write down this equation here. So the area relation A2 by A1 in terms of Mach number, you must have seen this. It's a huge equation. This is gamma minus 1 by 2 into m2 square divided by 1 plus gamma minus 1 by 2 m1 square. Have you seen this equation? So you've seen the area Mach relation, right? So from the area Mach relation, I've just got this from there. Right, so the area Mach relation which you've seen is that A star related to this. You must have seen when one of the Mach number is 1 and the other one is A star, right? A by A star relation you have seen. Yeah, so now what I'm trying to, this equation is basically when there are two different areas A1 and A2. So you have some duct, okay? Let's say we have some duct over here, and I have considered this section A1 and I've considered this section A2, okay? And the flow is like, let's say, isentropic over here. Then from A1 I can imagine a situation where A1 is taken to A1 star, okay? So that means whatever is the flow condition at A1, if I bring it isentropically to M1 equal to 1, So then I'll get what? I'll get A1 star, right? So you have that A by A star relation. You remember that? Yeah. Okay. So then similarly I can also take A2 to A2 star. You agree? Yeah. The flow conditions are different at A1 and A2. Both of them I can independently imagine a situation where in an imaginary process you are taking it isentropically to Mach 1. Right? So then we get our star reference state, which we have seen last time. Okay. So the next thing, if I use this condition, I will get A2 star by A1 star. So what I am going to do, I am just going to put M1 and M2 as value 1 in this equation. Okay, so when you evaluate that, you will get that A2 star by A1 star is nothing but equal to e power delta S by R, because all the other terms will just become 1, isn't it? Okay, so we have this equation. So what this means, if the entropy increases, then your A2 star will be more than A1 star. Now you go back and compare this to your delta P equation. What this means, if entropy increases, stagnation pressure will decrease. You agree? Okay, simple maths. Let's multiply both these equations. Okay, so what do we get from that? If I multiply A2 star by A1 star into P02 by P01. So that is A2 star by A1 star is e power delta S by R, and this is e power minus delta S by R, isn't it? So that gives me 1. Okay. So this equation turns out to be P01 A1 star is equal to P02 A2 star. So this equation will come very handy when we understand. So I'll be discussing today the operation of supersonic wind tunnel. Okay. So we'll use this equation that time. Do you have any doubts? So you understood this equation, right? You have seen this also. Okay. Okay. Perfect. So we'll start solving some questions now, if you don't have any doubts. Okay. Okay, so let's start with this simple question. Here I've considered helium, so I've also given you the gamma. Helium is flowing at a Mach number of 1.8 and it enters a normal shock. So basically a normal shock is created somehow. You have to determine the pressure ratio across the shock. So how do I start? Yes, so that equation is P2 by P1 is equal to 1 plus gamma M1 square by 1 plus 1 plus gamma M2 square, right? So you have information only of M1. M1 is given to you. Gamma is given to you. So what do you do? Using M1 you can find M2. How? Either you use the gas tables, right? You have direct relation, and how that relation comes in, you just have to use all the 3 equations that we discussed, right? So we had a pressure ratio, a temperature ratio, and we also had this P1 M1 under root T1, P2 M2 under root T2. So if you see in this equation, if you put the equation of P2 by P1 and you put the equation of T2 by T1, both these functions, they are functions of M1 and M2, right? So this equation will completely turn out to be a function of M1 and M2. Okay, so Do you have the equation? Will you use the equation or will you use gas tables? You can use either of them. You can use gas tables, yeah. Okay, so tell me what is the value of M2? Okay, till you solve it, for convenience, let me write that expression of M2 also. You can either use gas tables, always keep your gas tables handy, that would be better, or you can, how are you going to use the gas tables, by the way? Do you have gas tables for gamma equal to 1.67? Yeah, okay. Okay, so you're saying that M2 is, can you repeat, 0.6? Yeah, 0.9. Okay, so I can write 1 approximately. Yeah, this is fine. Okay, so now please calculate and tell me P2 by P1. We have the equation there. Yeah, that also you can get from gas table directly. I think you're telling me something else. No. P2 by P1. Yes, 3.8. Okay. Okay, so we'll move on to the next question. So the fluid is air, you can take gamma is 1.4, and if the conditions before the shock are given to you, you have to determine the conditions after the shock, and you have to also calculate the entropy change that occurs across the shock. Okay, so we have to find, so we are, let me write it down. We are given M1, P1 and T1. We have to find M2, P2, T2, and we have to find delta S. Okay. So for finding entropy, we have to go back to the relation of P02 by P01. So how do we proceed? Yeah. Okay, so from gas tables, you are telling me. Okay, gas tables gives M2 is equal to 0.577. Okay. Yeah, that is fine. .687. Okay, so that gives me T2 is equal to, just multiply it, yeah, so it's 844 degree Rankine. Okay, R is Rankine. So the questions that I have are in the they are in some other unit system, right? So yeah. Okay, and similarly you can also get P2 by P1. .5, right? Or 2.5? What did you say? Okay. Yeah. Okay. No, we don't need the density ratio. So we have P2 by P1. That is 4.5. Okay, so that gives me P2 is equal to, so you can just multiply P1. It turns out to be 90 psi. Okay. So now how do we find entropy you must also have the stagnation pressure ratio, right? Yeah. Yeah. No, go ahead. Yeah, so again from gas tables you can get this 0.72. Okay, so then what is delta S? Calculate and tell me. You know R for air, right? Yeah. You can tell me the value of delta S by R. Delta S you are getting 94 point. So this is in SI units. Can you also tell me delta S by R? 0.32. Yeah, that is fine. Okay, so these were simple questions. Let's do another one. So once you have the gas tables, it's very easy, right? Yeah. Okay, so I'll just reiterate what we have already seen, that as the strength of the shock increases, the losses will also increase. Okay, this is very important. So this delta S we calculated right now. So like you already understood that the Mach number was 2, so this was delta S. So if you do the same exercise and maybe start with M1 equal to 5 or something, then delta S will be much more than this. Okay. So now there's this question: air has a temperature and pressure of 300 Kelvin and 2 bar respectively. It is flowing with a velocity which is given 868 meter per second, and again let's say there is a normal shock. So you have to determine the density before and after the shock. Okay. So how do we find the density before the shock? Rho1 is equal to ideal gas equation. So we know T1 and P1, right? So Rho1 is nothing but P1 by R T1. So you can tell me the value of Rho1. Yeah, 2.32 kg per meter cube. That's fine. Okay, and now what do we do? Yeah. Right. So most important is that we have to find the Mach number, right? That is the main thing you have to calculate here. Okay, so you know velocity and you know temperature, so you can find A1. Gamma is 1.4, R is 287, and temperature is given. So you can tell me the value of M1, and there's an under root, don't forget that. Sorry, can you repeat? 2.5, that's right. Okay, so now from the shock table, gas tables, you can tell me P2. You can tell M2, P2 by P1, all these values. Sorry, M2 is 0.512. And you can directly find the density ratio, right? You don't even need to find pressure ratios. Yeah. 3.34, okay. So then you can tell me the value of rho 2. Rho 1 is 2.32, right? And that multiplied to 3.33 is how much? It's no, just check your calculation. Right. Yeah, what was the problem before? Okay. Oh. Okay, but this is the right answer. Maybe some calculation error. Okay. So this is the next question. Yeah. So oxygen enters a converging section. So I don't have the figure here, but let me draw it for you. So there's a converging section. Okay, and they say that a normal shock occurs exactly at the exit. Okay. Okay, now and the entering Mach number is given, so that means over here Mach number m1 is 2.8, and let's say this point is station 1, okay, and this point over here just before the shock is station 2, and they have also given us A1 by A2, which is 1.7. So A1 is more than A2 because it's a converging section. Fine. And now you have to compute all the overall static temperature ratio, that is T3 by T1. So this section just after the shock is 3. So if we have a shock, we know how to calculate the temperature ratio very close. So if you go back to your derivation, if you go back to this figure, remember that I said we can have a very general variable area duct, but what we are considering is a control volume which encompasses the fluid very close to the shock, right? Yeah, so all these relations that we have calculated, they are valid only just after and just before the shock. So if I can calculate temperature ratios T2 and T1 like that. So if I come back to this question that we have, you can calculate T3 by T2 using the shock relations, but they have asked us to calculate T3 by T1. Okay, so how do we proceed? First you have to calculate M2. Yeah. How do you do that? Yeah, we have the area ratio. Okay, so you are suggesting we use that relation which was defined here. I wrote it down as a huge equation. Yeah, this one. You can't use this because delta S is there and we don't know anything about delta S. Although you can take it to be 0 because you can assume the flow from 1 to 2 to be isentropic. Okay, so you can use that equation also. But it would be better if we use the A by A star relation. And if you go to your gas tables, for every Mach number you have A by A star, isn't it? Yeah. And we know M1. So if I know M1, is 2.8. Can you tell me what is A1 by A star? A1 star? Yeah. Check the table. Air, oxygen, but I think just check for air. What is it? .8 is not given in table. Okay, so for 2.75, how much is it? Okay, yeah. So so they have used gamma as 1.4 here. Okay, this value I'll give you right now. A1 by A1 star turns out to be 3.5. So now if you don't have the exact value, then what do? You go back to the original relation, A by A star related to M. Okay, and then you put in the value of Mach number 2.8 and you will get this A1 by A1 star. That relation you have, right? A by A star related to M, right? So okay, A1 by A1 star is 3.5. Now what do we actually want to find? We want to relate the Mach number over here. So I need to find A by A star over here, right? So I need to find A2 by A2 star. But I know A2 by A1 and I know A1 by A1 star, right? So, and what is the next thing? What are the ratios left? Help me out here. See, A2 by A1 and A1 will get cancelled. So A1 star needs to get cancelled and I need A2 star, right? You're seeing what I've done? Yeah. Okay. Now this ratio we have. Okay, this ratio we found by the area Mach relation. And we also have an equation which gives A1 star by A2 star. Which was what? We just saw it in the starting. So we derived this, right? A2 star by A1 star is e power delta S by R. And like I said, you can assume over here that the Mach number is, the flow is isentropic from 1 to 2. And whatever non-isentropic flow occurs, that is only due to the shock, right? So just before the shock, it is isentropic. So delta S is basically 0. Yeah, so A1 star by A2 star is 1. So A2 by A1, I know. A1 by A2 I know. So this is 1 by 1.7 multiplied to 3.5 multiplied to 1. Okay. So this is one method, or the other method could have been simply use the equation A2 by A1 related to M1 by M2, and there also you put e power delta S by R as 1. Okay. Okay. So in any case, we get A2 by A2 star as 2.06. So now can you tell me what is M2? You can take it either from the shock table, or you will have to solve the equation for A by A star related to Mach number. Yeah, so close by 2 is what is the next value given after A2 by A2 star? Okay. M2, how can it be subsonic? It is a converging section. Shock is occurring. M2 ahead of shock cannot be subsonic, right? So there must be two relations, remember? Two Mach numbers, because it's a quadratic equation. Yeah, so what is the supersonic value? So for the same A by A star, you will have one subsonic, one supersonic. If you remember, last time we solved a question with this. No, see, you go and check area ratio as 2.06. What are the two Mach numbers given? Okay, somewhere close to the value of 2.06. See, exact value will never be there. M2 is not given. Yeah. Yeah, that is right. So, what was the problem? Okay, no. So, see, my M1, M2 is according to this question, station 1 and station 2. Okay. In the gas table, you will have one subsonic and one supersonic values. So, you should see the question. Now, here the flow was supersonic and it comes to section 2. It remains supersonic. That is why there is a shock. So, what you had to do was, after finding this area ratio, A2 by A2 star, okay, you got 2.06. You go to the gas table. For that particular area ratio, A by A star ratio, you will see there are two Mach numbers. It can be some supersonic and subsonic value. So, you have to choose the supersonic value, isn't it? Okay. So, from the gas tables, you got this as 2.25. So, I'll take this as 2.25. Okay. Yeah, so this is fine. Now, what do? What did we need? We needed T3 by T1. So, first I need to find T3 by T1. So, what will we do? We'll choose M2 as our inlet Mach number for the shock and calculate the static temperature ratios. Okay. So, what is the static temperature ratio? First of all, what is M3? So, if we have a shock, right, on this side of the shock we have M2, on this side we have M3. So, can you tell me what is the value of M3? Yeah, that's fine. So, don't get confused with 2 and 3. Okay, what is the value? Yes, yeah, so this is fine, 0.54. And what is the temperature ratio now? Temperature ratio will be T3 by T2. Okay, so it is approximately 1.88. So you are getting 1.85, fine. So now what do? We have T3 by T1 is equal to T3 by T2 multiplied to T2 by T1. Okay, so we know T3 by T2. How do we get T2 by T1? continuity equation, how will that give us temperature? So remember 1 to 2, what is happening? It is an isentropic relation, right? Isentropic flow. So what happens in that? Exactly, stagnation temperature remains same. So I can say T02 is equal to T01, and I know T0 is equal to what? T into 1 plus gamma minus 1 by 2 m square, isn't it? Okay, so then what do we do? Can you find T2 by T1 now? We know M1, we know M2, isn't it? Yeah, so please find, yeah, so please find T2 by T1 and tell me. Yeah, gamma is 1.4, you can take. Yes. T0 1 divided by T1. Okay, T0 1 by T1 is 0.568. You can just give me the value of T2 by T1 directly. Okay, fine. Go ahead. T0 2 by T2 is? Did I write something wrong? 0.568 or 0.618? Sorry, what is this value? Okay. T0 1 divided by T1 is equal to, yeah, okay, and then T0 2 divided by T2 is equal to, okay, T2 by T1 is then, I think you did opposite, right? See, T2 is in the denominator here. One 1.276. Okay. Okay, so what do you get? T3 by T1? T3 divided by T2, we got 1.88. Yes. Okay, so let me write it fresh. Yeah, so T3 divided by T1, you are getting as 2.4. That is fine. That is correct. Okay, so any doubts in this question? You understood how we did it? You understood, right? Yeah. Okay. Most important was to understand 1 to 2 has to be taken as isentropic flow, and after that you use the shock tables, right? And this area relation. Yeah. The this is no. So first critical was when the flow is subsonic. Third critical was when the flow is supersonic. And this, what you are asking is when the shock stands at the exit, that is second critical. The diagram that we discussed that day, right? Okay. Okay, so we'll go to the next question. Hello, am I audible? Okay. Okay, so let's solve this question. So there is a, one second. Yeah, so there's a converging diverging nozzle which has an area ratio of 3.5. At off design conditions, the exit Mach number is observed to be 0.3. So we have to calculate what is the pressure ratio that will create such a situation. So remember, this is an off design condition. What is off design condition? Why are we saying it is off design? Because we want the CD nozzle to operate in a situation where the flow is isentropic throughout, isn't it? There are no losses. Okay, so we will get a shock only when it is off design condition. So basically what the question says is that in the CD nozzle there is some place where a shock is occurring. Is that clear? Yeah. So how do we proceed? We don't know. Yeah. We don't. Yeah, we don't know the location of the shock. Yeah, so can you tell me how will you start? Okay. Just one second. Okay, so we are given area ratio. So let me first consider a converging diverging nozzle over here. So what is the what is defined as the area ratio of a CD nozzle? Yeah. Okay, so let's say this, let's call this the exit and this is my throat. So the AE by AT is given to me, which is 3.5. And okay, let's say somewhere there is a shock and I don't know the location, and the exit Mach number is 0.3. Okay, so I can say this Mach number is ME, which is 0.3. Okay, so we have to find what? Pressure ratio. So what is the relation, one relation we saw, which relates areas to pressures? I discussed that relation. So if you go back, this is the equation, the stagnation pressure and the star reference areas. So we found the relation between them, right? Okay. So I can use this equation over here. P01 A1 star is equal to P02 A2 star. And if I know the area ratios and the Mach number, I can find the star reference areas. Okay, so let me, do you want to try or should I tell you the solution? Okay. Okay. So let me do some numbering to this CD nozzle. So, okay, so let us say that this throat area is, so the inlet was 1, the throat area is 2. Okay, let's say the shock is occurring somewhere over here, right? So just before the shock, I'll say is section 3, and just after the shock is 4, and the exit is 5. Okay, so this AE by AT is nothing but A5 by A2, right? So in this numbering system, and this ME is M5. Okay. Okay, so now we can write this equation P5 by P05 multiplied to A5 by A5 star. So if you go to the gas table, in that check for Mach number equal to 0.3. Do we have this ratio? Yeah. So you have A by A star ratio and P by P star ratio, isn't it? Oh, P naught. Yeah. This is. So you can tell me the P by P naught ratio and A by A star ratio first. Yes. How is that possible? You're saying Mach number 0.3 is not given. Okay, so then why don't you calculate? So you have P naught and you have the relation P by P naught. So just do this calculation. P naught is equal to P into 1 plus gamma minus 1 by 2 m square to the power of gamma by gamma minus 1. And you have A by A star. So I don't exactly remember the relation of A by A star with Mach number. You have that relation, right? Can you tell me the equation? One divided by m. Yeah. 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 Okay. Yeah. 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 Gamma plus 1 divided by 2 times gamma minus 1. This is right, isn't it? Yeah. So please go ahead and calculate P naught by P and A by A star when Mach number is given, and tell me this value. So you can start with telling me what is P naught by P when Mach number is 0.3. Yeah. Okay. And A by A star? Yeah. Gamma plus 1. Okay, thanks. Yeah. Okay, so A5 by A5 star is equal to 2.035. Okay, that is pretty large. Okay, fine. So if you just multiply and get this value, so remember this is P naught by P, so you will have to multiply here 1 by 1.064, multiply it to 2.035. So what do you get? No, see what you have to do. I think you have multiplied both the values. It's P naught by P, we need P by P naught. You have to divide them. Yes, perfect. Okay, so we got this value. Now what do I need? So if you go back, you have to get the pressure ratio, which is P5 by P1, right? And the operating pressure ratio is nothing but P5 by P1. But if you remember, we always take this as the inlet pressure as a stagnation pressure, right? So P1 is nothing but P0. Okay, so what we have to find is P5 by P01. That is my operating pressure ratio. And I have P5 by P05. So what do I do? Yes, exactly. We'll do the same cascade. So I can write this as, so I can write P5 by P05 and then multiply to P05 by P01. Okay, and I can find this pressure ratio only based on my area ratio, because if you remember, whenever there is a shock, across the shock I know that, let's say P0 downstream of the shock and A star downstream, that is equal to P0 upstream of the shock, A star upstream, isn't it? Yeah, so that's why I need here my area ratios. So I'll multiply to P05, I'll multiply A5 star. Okay, and to P01 I'll multiply A1 star. Now and then obviously I have to counter it, so I'll have A1 star, and remember I have the ratios here, so this is A5 star here. Okay, and I'll also multiply A2 by A2. Okay, why I'm doing this I'll explain, but if you come back here to this diagram, from 1 to 3 the flow is isentropic. Only across 3 to 4 I can apply this equation, that is P0 4 A4 star is equal to P0 3 A3 star. But what I have done, I have used stations 5 and 1. So how do you justify that? So 4 to 5 it is going to remain the same, right? There is anyways the flow is isentropic, so there is no loss, so the stagnation pressure is not going to change. A star is not going to change. So if you remember that A star ratios will change only when entropy change occurs. So 4 to 5 there is no change, and 1 to 3 there is no change. So whatever ratios I can apply for 4 and 3, I can also apply for 5 and 1 in this equation. Did you understand that? Did you understand this? No? Okay, so can I write this equation? I have a shock, so let me just add a page here. See. Okay, so I'm having a shock which is over here. This is section 3 and this is section 4. Okay, so we know that P04 A4 star is equal to P03 A3 star. Right? Now come back to this derivation. What is A2 star by A1 star? E power delta S by R. So if I apply this equation, now we had an exit, and at that exit was section 5. So between 5 to 4, if I have to apply A5 star by A4 star, that is equal to E power delta S by R, but the flow is isentropic from 4 to 5. So this is 1, you know, and then the next thing I can do is from 1 to 3. So from A1 to A3, again I can apply the equation for star areas, and that is again E power delta S by R, but the flow is isentropic in this part of the CD nozzle till where the shock has not occurred, isn't it? So again this is 1. This is clear? So that is why I can take, instead of taking the ratio between the sections 3 and 4, I can take the ratios between sections 5 and 1 directly. The same concept holds for P0 also. So can I say P05 is equal to P04? Yeah. And P03 is equal to P01? Yeah. So instead of taking this, applying this equation at 3 and 4, I will apply this equation at 5 and 1 directly. Okay, so that is over here. Okay, so if I just rearrange this and write once, so I can say P5 by P05 multiplied to A5 by A5 star, and that multiplied to P05 A5 star by P01 A1 star. Okay, one second. Okay, this first step was clear, right? So I have only introduced this A5 by A5 star right now. And then this is obviously going to be 1. And then I have A1 star by A5 star. So instead of that, I can say A1 star by A2 multiplied to A2 by A5. Okay. So now we know this particular value. We found this value to be, let me change the color so it's easier. So this value we found to be 1.91 or 1.92, right? Okay. And this is going to be 1. Correct? Okay. And do we have the area ratio A2 by A5? Yes. So that was given to us, which is 3.5. That is why, so if you were wondering why I introduced this 2, that the reason is that we are given the relation to the throat area, isn't it? So that is why I introduced this A2 over here. So A2 by A5 is given to me as 3.5. And now if you check for A2 by A1 star, it is going to be same as A2 by A2 star, because like we saw right now, if there is isentropic flow, the A star is going to remain same, isn't it? So from 1 to 2 it is the same. So here I can write this A1 star by A2 is nothing but A2 star by A2. And what is that going to be? How do you find that? So let me write clearly over here. What is A1 star by A2? It is equal to A2 star by A2. And A2, what is section 2? It is my throat. What happens at the throat? Sonic flow. Right? So the flow is sonic. So what is the value of this going to be in your area Mach relation? 1. Isn't it? Did you understand this? Okay, so the flow is sonic at the throat. So I will get A2 star by A2 is 1. So now what is the answer? Yeah, just note that what is given to us is A5 by A2. So I think I've written something wrong there. Yeah, A2 by A5 is 1 by 3.5. So this is 1.91 by 3.5. Yeah, 0.546. Okay, so did you understand this question? What did we do here? So this was comparatively a tougher question. So let me just go through it again, just the steps. So what is given to us, first of all, it's a CD nozzle and they have given the area ratio. So for a nozzle, we should know area ratio is exit area by the throat area. Okay, so we wrote down this A5 by A2 is 3.5. And they have given it is at operating at off design condition. Off design condition is when shock occurs somewhere inside the CD nozzle. Okay, and they have given us only the exit Mach number and we have to find what is the pressure ratio. So we don't know the location of the shock. We don't need the location of the shock. What we need is only this one relation. So this was the most important relation that you needed. And the other thing was to use this cascading concept. So you have to do the cascading between the pressure ratios and area ratios. So what did we do? We said that from 4 to 5 it's isentropic flow. So P naught is not going to change, A star is not going to change. From 1 to 3 again it's isentropic flow. P naught is not going to change, A star is not going to change. So what is going to change? Only the static conditions. Yeah, so instead of using the static conditions, we'll use these P naught and A star ratios. So first we defined the only condition that we need, P5 by P05 and A5 by A5 star. Why we can define this? Because we know the Mach number. Okay, because the Mach number is given, I can find P0 by P and A by A star. Okay, so we found this relation. And then for the operating pressure ratio, which is P by P0, P5 by P01, I will use this P5 by P05, A5 by A5 star. These are the values I know. And I also know the throat area ratio, A2 by A5, throat and exit area. So that's why we included this particular value A2 over here. Okay, so you should be able to write this kind of a cascading ratios to get your operating pressure ratio. So just after the session, just try and think about it once on your own. How do you come up with these ratios which will cancel out each other and give you the operating pressure ratio? Okay. Do you have any doubts here why we took 1 in any of these situations? Okay, this, yes. Okay. Okay. Okay, that's good. Yeah. So, but did you know this P0 A star relation? Were you aware of that? Yeah, this. this relation. This is a very important relation. Yeah, so we will use it to understand supersonic wind tunnel operation now. Okay, do you have any doubts about this question or any other question we did today? No. Okay, so then let us understand the operation of a supersonic wind tunnel. Okay. So you must have already seen this supersonic wind tunnel. Can you tell me, there are two figures here, which one is the operating condition and which one is not? At the test section we have a shock wave, that is operating condition, or sorry, right. Okay, what is operating condition? What is operating condition? Okay, so you are saying this is the starting condition and this is the operating condition, means where I basically put some maybe wing over here or airfoil over here and I actually check what happens if supersonic flow is going over it, right? So I don't want a shock in the test section when I am operating. So this is the operating condition, ideal situation that we want. Yeah, and this is the starting situation which actually happens. So why does it happen? Why do we have a starting problem? Why do we get a shock over here? So you know how a supersonic wind tunnel starts? We have this exhauster, there's this huge fan, it starts rotating. So when the fan rotates, what is it going to do? It is going to create lack in pressure in this region, right? So that will create a pressure ratio across this entire wind tunnel, and as a result your airflow will start moving. Okay, so when the flow moves at very high speeds, if you start decreasing pressure, first it will be subsonic throughout, but as you decrease the pressure further and further, so if you remember that particular diagram where we said that the receiver pressure or the pressure ratio determines whether you are operating at first critical or second critical or third critical or somewhere in between. So basically when you come out of the Venturi regime, then you remember the Venturi regime, right? So then as soon as you cross the first critical point, you will start getting shocks. So you are decreasing the pressure continuously, right? The fan speed is going to be increased continuously. We cannot suddenly go to a certain fan speed. So as a result, what will happen? The pressure ratio is going to decrease suddenly. Continuously. So let me just draw that diagram just to remind you. Sorry. Okay, so we had this. This is the X location along a converging diverging nozzle. Okay, simple CD nozzle. And we had the pressure ratio. So initially the pressure starts declining and then it increases if the flow is subsonic, and then if I keep decreasing the pressure, this was the supersonic isentropic case, which was my third critical. This was the first critical, and the second critical was if at the exit I have a shock. So this is my second critical. But what we are doing, this is my pressure ratio. I am decreasing the pressure ratio, the receiver pressure, I am decreasing it continuously. So I cannot expect to jump suddenly from the first to the third. Ideally I want to operate at third critical, and that is never going to happen. You can never have a supersonic wind tunnel where there is no shock, isn't it? You know this? Yeah, the shock will always sit in the diffuser. There will always be a shock. You cannot avoid it, because once it has come, you cannot remove it, how much ever may you decrease the pressure. And this, if you see in the diagram itself, this pressure ratio, which is at the third critical, is so low. You have to achieve such a low pressure ratio, that itself is very costly. it is very expensive to reach such low pressures. So we will avoid operating at the third critical. Is that understood? Expensive in the sense in operating. I mean, see, if you have to create low pressures, what are you doing? You are running a fan at very high speeds. So first of all, if you start running a fan at very, very high speeds, there will be shocks near the fan tips itself. Okay, so we have to avoid a situation where we have to create very low pressures, which is where the third critical will occur. So we cannot operate at the third critical. And once the shock has occurred in the wind tunnel, you cannot remove it. You can only maybe settle it at some point. Okay, so what we do is we keep decreasing the pressure by increasing the speed of the fan, and as soon as you cross this Venturi regime and you come into the non-isentropic flow, you will get a shock, and the first shock will occur at the throat, and it will occur at this throat. Why it will occur at this throat? Why the shock will occur at the first throat? It's very simple. After that, sorry, can you repeat? Yeah, the question is, see, I have a, if you see the structure of this wind tunnel, there is a throat over here, section 2. Okay, this is a throat. This is also a throat. So shock could have occurred anywhere. The shock will occur at the location where the area is minimum. We know that. It will start occurring after that. So first of all, understand that the flow is moving in this direction. Right? So whatever has to happen will first happen around this throat. Another thing is this A2, we will discuss why, but this A2 is lesser than A5. Okay. Pen is not working. Yeah, A2 is lesser than A5. Okay, so we will discuss why this happens. But anyways, this area is minimum as compared to any other section. So the shock will first occur over here. Okay, and then the shock will move downstream as you further decrease the pressure. Okay, yeah. And when the shock happens to be in the test section, that time we will have maximum losses. Why? Because see, over here the area is increasing. When the area is increasing, you will see that the shock strength is going to increase. Over here, the shock strength is going to be maximum. So there will be maximum losses. So we have to very quickly swallow the shock into the other throat. The reason why this throat exists over here is to swallow the shock. That is the purpose of this second throat. Okay. Yes. Yeah. Yeah, so that's first thing that I said was no, it is difficult to operate at such high speeds. Another thing is, if you move the shock anywhere beyond this, again the area is going to increase, isn't it? And again the shock strength will increase. Then again more and more losses. After the throat of diffuser, yeah. Yeah, that subsonic flow doesn't matter, no? What matters is the pressure ratio and the strength of the shock. So the further you decrease this pressure, you are basically increasing the inlet supersonic flow, Mach number. And that is what determines the shock strength. And then this, if the shock moves further downstream, how will it move further downstream? Only when you create more and more lower pressure here. Lower and lower pressure. So that is going to increase the strength of the shock, plus the area is increasing, the shock strength is increasing. you telling me that if any shock exists and there is a subsonic flow here, the shock is going to go and vanish into the subsonic flow? Why does the shock exist in the first place? Are you getting it? How can the shock, see, you are saying there is subsonic flow here. Okay, let me draw something. So I'll copy this. Yeah. You cannot eliminate the shock. That's what I'm trying to explain. The shock will not, the shock will always be there in the diffuser throat. It will not disappear. What is going to happen is that the shock, what you are talking about, the shock elimination, you have to eliminate the shock from this test section. It should never occur in the test section. What do we need in the test section? Supersonic flow. Okay, but the shock will always be there over here. Okay. Yeah. So now I want to actually draw the Mach number variation along this wind tunnel. So let me do that. That will also clarify some of your doubts. So here I'll plot the Mach number m, and this is the location. So I'll just say this is x, or position in wind tunnel, and this is continue to 1. This is the section 2, 3, 4, 5 is the diffuser throat, and this. Okay. So what, let us say there was subsonic flow. We are trying to create supersonic flow, isn't it? So the inlet is going to be subsonic. In general, so are you saying something? Yeah. Yeah, at the inlet we have, I mean, see, you are going to operate the supersonic wind tunnel on ground, and on ground that flow is just stagnant, or it's just going to be subsonic, right? You are going to draw air from the atmosphere. This is open to the atmosphere. Okay, so this flow, yeah, right. Okay, yes, yeah, you can have a closed wind tunnel also, but what I'm talking about is the open wind tunnel right now. Yeah, okay. So this Mach number is going to be very small, but as soon as you start coming into this converging diverging part, the flow will start, the flow speed is going to start increasing, right? So in the CD nozzle, let us say the Mach number increases, and the shock is sitting in the test section, right? So in the flow becomes sonic, m equal to 1 in nozzle, and then it will become supersonic in the diverging part of this. Okay, so then again the Mach number is going to increase further, and it will remain up till the point of, up till this point of the shock location. It is going to remain almost constant, and as soon as the shock occurs, this will drop. Okay, so let us say Mach 1 was here, which is the point at which the throat of this nozzle occurs. Okay, and after that, after the shock, the Mach number is going to drop dramatically below 1, isn't it? Somewhere here, and after that it will remain almost constant in the test section, and then what happens in the CD nozzle? Again it is going to increase. Again the flow speed is going to increase. Do you understand this? Yeah, and ideally in the diffuser it should reach Mach 1. So I should probably redraw this. So we want to reach Mach 1 here, but after this the flow should be subsonic. So over here we want to operate at the first critical, so it will just decrease. So do you understand this diagram? Is this clear? Any doubts anywhere? No. So this is when it was the starting condition. What happens when the shock is actually sitting in the diffuser throat, when we have the operating condition, right? So I'll draw the shock here, and let us draw the variation of the Mach number. Okay, so or maybe I can just copy paste this diagram. Okay, so here I'll plot the Mach number, and this is the location. Okay, so now what do we have? We have a shock in the diffuser throat, and again the inlet is still subsonic, isn't it? So can you help me? What is going to happen to the Mach number? Maybe I'll draw here itself so that you can compare. Yeah. So again the Mach number is going to increase. It is going to increase up to 1 here, after which it will become supersonic, and it will remain supersonic throughout the test section, right? And what happens in the diffuser part? So now see, the flow is supersonic and this part of the wind tunnel is converging, so it is going to act like a diffuser, right? If you remember, when Mach number is more than 1, yeah, converging section is a diffuser. So then the Mach number will start decreasing, and then we have a shock. So immediately there will be a drop from here below M1, below Mach equal to 1. Okay, and after that the flow becomes subsonic, and what is going to happen now? There is a diffuser, the diverging section, and in the diverging section what happens to subsonic flow? Velocity decreases even further, and then it almost becomes constant in the exhaust. Okay. Yes. Yeah. Yes, this shock is going to be weaker as compared to the shock which stands in the test section. That is right. Yeah, so ideally, yeah, you're right. So I should maybe make that clear. Yes, so maybe the drop I should show is lesser, isn't it? Yeah, you're right. Okay, so here I will plot something else. I'll plot the static pressure variation. So what is going to happen to static pressure? What is going to happen to static pressure over here? We are talking about operating condition. Okay? Yeah, the pressure is supposed to decrease continuously in this converging diverging part. So initially it is almost same. Okay, here it starts decreasing. It is going to decrease up till the test section, isn't it? Yeah, so So I'll decrease it up till the test section, and then it remains constant in the test section. What happens afterwards in the diffuser? So okay, what is no, so we have a supersonic flow in a converging section. What is happening to this supersonic flow? The Mach number is decreasing, right? Yeah, so pressure will increase, the static pressure is going to increase, and then you have a shock. So there is going to be a sudden increase in the static pressure, okay, and then it is going to increase further because the flow has become subsonic, but now we have a diverging section. So again the flow is going to the static pressure is going to increase, and then it will almost remain constant. Okay. Yeah, so I will let you do on your own the variation of static pressure during the starting problem. Okay. If you have any doubts, you can ask next time. Okay, so now there is another one concept. So we discussed starting problem. The next question is, what should be the area of these two throats? So we have two throats, 5 and 2. Now I am claiming that A5 should be more than A2. Do you know why? Yes, so we can write that. So let me say P0 5 A5 star. Can we write this, by the way? So let us go back to the diagram. So in this diagram, if you see, the shock is we can even start with the starting situation. The shock is over here, right? So I can always relate any of these test sections, any of these sections 4, 5, 6, 7. They are all going to have the same stagnation pressure and same, not 7, okay, 4, 5 and 6. They are going to have the same stagnation pressure and same A star. Do you agree? And similarly 3, 2, 1 will have the same P naughts and A star. When it is in the operating condition, then 1, 2, 3, 4, they will have the same P naught and same A star, and just after, so I will call this as 5. So just after the shock, 5, 6 will have the same P naught and A star, isn't it? So I have to compare 5 and 2. So I can write this relation: P naught 5 A5 star is equal to P naught 2 A2 star. Okay, now what? Yeah, so we have a shock. No matter whether it is sitting in test section or in diffuser throat, we get a shock, and P0 5 is going to be lesser than P0 2. Yeah. So obviously we should have A5 star should be more than A2 star. But if you also notice, what did we say? We want to operate at Mach 1 in the nozzle throat and the diffuser throat. And why do we want to operate at Mach 1? I could have operated at Mach 2, right? Why? Yeah. Exactly. So we'll have a stronger normal shock and we will have more losses. So we would like to be very close to Mach equal to 1. So that means this A2 star and A5 star is nothing but the A2 and A5 that I actually need. So A5 should be more than A2. So that is the first condition we have understood. Okay. How do I find the A5? How do I find what should be this value of A5? So I know what stagnation pressure. See, I know the test section. I know what Mach number I want to operate in the test section. So I know the pressure, stagnation pressure over here, P03, which is nothing but P02. So I know P02. I know the Mach number. So you can get a question like this. So there's a supersonic wind tunnel and you know Mach number that you want by design in the test section. Okay. So you will have P0 phi by P0 2 ratio. Is that understood? Yeah, so in the test section we know the design Mach number, so and we also know the stagnation pressure ratios. So we have the area ratios, so we know how to design our supersonic wind tunnel. Okay, obviously if I get this value A5 by design, so let me call this as A5 minimum, because this is the minimum A5 I need to be able to start the wind tunnel. If A5 is more than A5 minimum, what happens? See, if A5 is more than A5 minimum, then ideally I wanted Mach equal to 1 over here. I'll get higher Mach numbers. Do you agree? Okay, so here in this situation I'll get higher M. M will be more than 1 at diffuser throat. Now what happens if A5 is less than A5 minimum? What happens if I make, see, I know by design, I started imagining I want a test section with some Mach number, and I know the stagnation pressure ratios. I know I have fixed A2, okay, I have already fixed A2. So I calculated A5 minimum A5 that I need to satisfy this condition, this particular condition. Okay, so I know A5 that I need. But what if I make a wind tunnel with A5 which is less than A5 minimum? What is going to happen? Any idea? The shock wave will not. Why? See, we need a minimum A5 to be able to start the wind tunnel. If we make it lesser than this, the wind tunnel will not start. Will not start as in the flow is not going to occur. There is going to be choking. Okay, so okay, let us understand like this. What happened in the starting condition? In the starting condition, first, because A2 was smaller, okay, the flow started choking over here, and the shock started occurring here, and then as you decrease the pressure further, the shock moved ahead, right? But if A5 was smaller, then the choking will happen over here first, and the shock will start occurring at A5. The shock will never occur at A2. Now you will say, okay, that is ideal condition, the shock will never move through test section, isn't it? Then what is the problem with this? It's a very fundamental problem. Why don't I want the shock to occur at diffuser throat first? So A5 less than A5 minimum, okay, I will get a shock first at diffuser throat. What is the issue with that? Just think, how does shock occur? Okay. No idea? Okay, see, if the shock occurs first at A5, first time at A5, so let me draw that condition for you. So that means I have a nozzle here, a throat here, test section, and then another throat here, okay, and I am drawing this area to be smaller. So this throat area is large and this throat area is smaller, okay, and the shock has to occur over here. So first the flow which was coming in was what? Subsonic. Okay, so if the shock is not going to occur here, that means the flow never reached sonic value here, or even if it reached sonic value, the flow is maybe sonic here, but after that it is again subsonic. So that means this throat, the second station in the nozzle, that is going to operate in the Venturi regime, right? So in the test section I will always have subsonic flow. So if the shock occurs first time at 5 in the diffuser throat, then the flow is going to remain subsonic always. Then what is the point? We are not going to have a supersonic internal, right? Yeah. So this is the problem. Okay. Okay, that's all I have for today. Do you have any questions? Okay. Okay. So maybe you can ask questions about the normal shock part first, if you have any questions about normal shock. Okay.